I'll just quickly write the conclusions. Imagine I have a curve in space. So it's like curve. So it's like a circle in space actually. And my frame is moving on the circle. Okay? What would be your observation? Without computation, let's have some, what do you call, intuitive feeling for it, basically. So imagine I have a circle, okay, and my frame is moving on the circle, okay. So the tangent is going to be along the circle, normal is going to be inward circle, okay, to the center of the circle, and binomial is going to be the perpendicular to the plane. Okay? Are you getting the point? What would be, think about it, what would be, so here's a fundamental question, what would be the relationship, roughly, between the curvature and the circle actually? Okay, let me not tell the key term. What would be the relationship between the curvature and circle? Think about it. If you have a small circle and you are moving it, what will happen? And if you have a big circle, okay, and your T and B frame is moving on it, what will happen actually? So take this.
So curvature decrease.
Smaller the circle.
Curvature. Sir, जब small circle होगा curvature ज़्यादा होगा.
Exactly. So it's like you have to change things rapidly. Okay, but if you are on a circle which is a huge, what do you call, radius, okay, then the turning is going to be slow. Are you getting the point? How about binomial? What will happen with the binomial? So it stays same, so it's constant. It doesn't change actually. So the torsion must be zero. Okay. So from this, what we observe roughly is that if you have a circle and you want to compute the curvature and torsion of it, the curvature is going to be more if the radius is smaller, and if the radius is big, the curvature would be less. So kind of they are inversely proportional to each other. So this is our intuitive mental picture basically. Okay. So let's see that the mathematics agrees with it or not. Okay. So imagine, obviously curvature is a plane curve. So imagine it's embedded in xy plane. So how does it going to look like? So it's like the beta of s is going to look like. So it's going to look like r cos t, r sin t, and 0. So it's going to be something like that. Sorry, S.
I was asking, ये मतलब यहाँ पर हम पैरामीटराइजेशन मतलब फिक्स कर दिए आपकी वजह से।
Yes.
अगर चेंज करें तो ये के पार्ट ऑप्शन चेंज होंगे। Parameterization.
No.
So it seems we can
क्या मतलब?
beta of s will be changed then.
Formula would be changed. So there will be change in the formula. But we will do also, the part about that when the curves are arbitrary, not the parameterization. But this is the key information because we know that every curve can be, made into or converted into. Imagine I have an arbitrary circle. Okay, let's not take the unit speed parameterization. Let's try to find the unit speed parameterization of it. So how can I find the unit speed parameterization? For that I have to compute beta prime of t, maybe let's call alpha, and then beta as the unit speed parameterization. So you need to compute alpha prime of t, so it's going to be minus r sin t, r cos t, 0. Okay? So the magnitude of this is going to be simply r, the magnitude of this guy. Okay? And if you integrate it, okay, from, for example, say 0 to t,
You will have
Okay.
RT.
0 to t, 0 to dt. What you're gonna get? You're gonna get arc length.
S is equal to R theta.
Okay. So you get S equal to
RT.
Rt, and therefore T is going to be S over R. Okay. So the unit speed parameterization of the circle is going to be R cos S over R, R sine S over R, and 0. This is going to be the unit speed parameterization. Okay. And then I have these formulas. I can easily compute two derivatives and then compute the magnitude. Okay. So it turns out, I'm not doing calculations. It turns out that if you compute the kappa for this unit speed curve, it turns out to be, as per our expectation, 1 over r actually. So what can I do with that? I can take 2 times derivative of this and compute its magnitude. Okay? It's not going to change anything. So cos is going to become sine and then become going to cos again. Okay? And then similarly, the other. Okay? So kappa is going to be 1 over r. And how about torsion? So if you compute the torsion of the curve, it's going to turn out to be 0. Okay? So what does this information is telling you? So we're going to prove basically soon a theorem is going to tell us that if a curve has a torsion 0, then it must be a plane curve. So it must be sitting in plane. So there is no twisting in it. Maybe there is curving but not twisting. Okay? Is it making sense?
So जरूरी है एक्स बार प्लेन हो
कोई भी हो सकता है. It must be in
space
plane.
में कोई भी.
Even it could be a space actually.
Yes.
Okay, but it doesn't have twist actually. So it's going to be, in some plane.
Planar curve.
हाँ प्लेन.
This is going to be a planar curve. ठीक है? Is it making sense? Okay, I would like to recommend that read the description that you have in book or maybe in the notes actually, okay, of all these things. So there are lots of intuitive pictorial things that have been told by the author. So, just read it.
Eta double derivative with magnitude. Kappa आपके पहले के बारे proposition.
So again you have to keep in mind, okay, that these are the formulas to compute. So just need to take 2 times derivative and magnitude. Compute cross product, dot product and divide it. So the good thing about these formulas is that you don't have to go here and there and compute T and N and B and then their derivative and so on and so forth. So you can compute it directly. Okay? That's a little proposition, but maybe something important from physical point of view. Okay? So if I treat alpha of t as a curve traced by a motion of the particle, or maybe a particle is moving along that curve. So you're going to always, or you can ask actually, that what would be the velocity of that particle in the terms of this Frenius-Array apparatus. Okay? So can I know the velocity of the particle using Frenius-Array apparatus? Can I find the acceleration of the particle using Frenius-Array apparatus? So if I have been given tau and b, can I know all these things? Okay? So proposition. So imagine I have a curve alpha from I to R3 Rn, whatever, with Frenius-Array apparatus, T and B and kappa and S, and V is the velocity of the curve, then you can compute this velocity, okay, by computing what? By computing the speed of the curve and multiply it with the tangent. Okay? And how are you going to compute the speed of the curve?
Magnitude of tangent.
Just take the magnitude of the velocity. Okay? And how you can compute the acceleration of the curve, or maybe acceleration of the particle. So it's going to have two components actually, one tangential component and other normal component. Okay? So the tangential component of the curve is going to be obviously speed. Okay? And the normal component of the curve is going to be speed square times kappa. Okay? So it's going to be kappa. Alright? This is arbitrary. What would be the quick proof of this curve? These two facts. So what is V? The velocity is alpha prime of t. Okay? But imagine now that I have a unit speed, what do you call, parameterization of the curve alpha of t. Then how does alpha of t is going to look like? Is going to be the beta of s of t at. This is going to be beta composition something. That is going to give me the alpha. Are you getting the point? And if I have this, what would be its derivative? So I can compute it using this. So it's going to be beta prime of s of t
and s prime of t.
S prime of t. Now S prime of t is what?
Velocity.
So that's your velocity, small v, speed. Okay, the magnitude of the velocity. And what is beta prime? So that's your t at. Okay. And verify this for yourself. Pretty.
उसको सिर्फ differentiate करना पड़ेगा velocity value.
Yes. So that's what you have to do.
Product rule.
Yes. Okay. So verify it for yourself. So why this proposition is interesting? Because it tells you that not only this Fresnel apparatus has importance, okay, from the perspective of geometric, but it also has what you call a mechanical importance as well.
Sir,
and interestingly, in order to compute the velocity and acceleration, you don't need binormal and torsion thing actually. So you can compute all this purely using tangent, normal, and curvature actually. So this is also an interesting thing to observe. Are you getting the point?
Sir, I was thinking कि हम क्या physically उसको देख सकते हैं acceleration के दो component होते हैं velocity का दूसरा component normal direction क्यों नहीं?
Because velocity has nothing to do with normality. So when you are moving only tangentially. Okay. So it's the change in the tangential what do you call component that is going to give you the velocity. Okay. Are you getting the point? Think about it. Imagine, the particle is moving on circle. Alright? This dv is going to dt is going to represent what? Is going to represent that the particle is moving tangentially. So that's the acceleration of the component, which is what do you call tangential. And what does this guy is going to represent?
Inward.
Okay.
Centripetal.
So it's going to give you Centripetal acceleration.
Centripetal acceleration.
So what's centripetal acceleration? So we know that A at the moment are what we call the normal component of the acceleration is this V square K, where K is kappa. But V kappa is what? For the circle. So it's V square over R. So it just really meet with our intuition actually. So it meets with the physics. That's what the physics does. Okay. But you're not doing something unusual. So let's move on. Let's have some more consequences and think about some more consequences of. What does this thing represent? You know, let me comment a little bit more on the observation that we have. So imagine, so what does this thing is telling you? Imagine you have a curve, okay? You have a curve, which is alpha of A. So we try to make sense. Let's use all this and analyze different things. Okay? I have a curve. And on curve, so I have velocity, okay, and velocity is tangential. Pretty simple, okay. If there is a relationship of this circle and the curve actually, so this is your tangent, and you're going to have a normal component. Maybe a normal vector also. So that's your normal vector. The curve. So this result is telling you that this normal vector is not a normal vector to the curve, but I can also see this as a normal vector to a circle. Okay? If you draw a circle. So draw a circle, okay? Draw a circle that, what do you call, fits in this, what do you call, the curve. What kind of measure, roughly this circle is what, the change in curve, okay, the change in tangent, okay, on this curve is same as the change in tangent on this circle. So roughly what you are saying, that this part of the curve can be approximated by the circle. Can be approximated by the circle. In such a way, the tangent vector, that is the tangent vector to the curve, is going to be the tangent to the circle that approximates the curve. Okay? And the normal vector, that is a normal vector to the curve, is going to be the normal vector of this circle. Are you getting the point? And if at this point you want to compute the curvature of the curve, then what you can do, so one way is that, compute this oscillating circle, we call this oscillating circle, okay?
And its radius.
And compute its radius.
1 over r. Yes.
So it's going to give you the curvature. This plane, Tn plane, okay? This Tn plane is called osculating plane again. Okay? Osculating plane. And this circle that lies in this osculating plane, you call that as osculating circle. So that's another osculating circle. So what's the good thing about osculating circle? That if you want to find the curvature, okay, of a curve at a particular point, take that point and take two other points, for example, the neighboring point of that curve, and try to fit a circle that fits in, those 3 points. And then try to compute the radius of that circle actually. So it's like this. And then the radius of circle is going to give you the radius of, the curvature basically. It's allowing to give you the curvature. And that curvature is going to be what is going to be the reciprocal of the radius of it. That's called the osculating circle.
If curvature is 0, then what would be interpretation of the circle?
What do you mean by that?
Means if at a particular point we have curvature 0.
So there is no change in this. The tangent is parallel to the
circle
all the time. This is straight line. Are you getting it? How about, so here's another thing. So here you have a small circle approximating the curve, and hence you have a more curvature. So you can say that, okay, you have a small radius and more curvature, because there is an inverse relationship between curvature and. How about if I try to draw a same kind of a circle here at this point? So you have this point, take what you call neighboring points and try to fit a circle around it, and that circle is going to be big now as compared to, what do you call, as compared to this one. And what does this shows? That you have a less curvature here because you have a more radius here. Are you getting the point? How about here, if you want to draw a circle, so it's going to be the bigger actually, and maybe the bigger. So it's like here, things are narrower, so you're going to get a smaller curvature. Yes. So the normal is going to be negative in this case. Is it making sense? Okay. So that's another way to do the geometry. We're not getting into it, but at least you must know. So, so it's like what we can do essentially, that give me a point on a curve, and then, I can draw basically a circle that approximates that curve in the neighborhood of that point. And then, since I have the equation of the circle that approximates the curve, I can find its radius. And that radius is going to give me the curvature of the curve. Okay? It's just, what do you call, another way to look at the things, okay, from a physical point of view. I'm not getting into it that how to find the osculating circle. I mean, if you are interested, you can find it in Barrett O'Neill, that how to find, so take a point and how to find the equation of oscillating circle. So there are certain formulas that you can use to compute it. Okay? Let's take another example. The next example is helix. What is the parameterization for helix? So beta of S is A cos omega S over C. So this is what that we have computed in, and A sine omega S over C, B S over C. Okay? And C is what? C is the square root of A square omega square plus B square. Okay? So in last lecture we computed this. I'm not computing it, you have to compute it for yourself. But if you will compute the curvature of this, what do you call, helix, you're going to get omega square over a square omega square plus b square. And then actually it would be plus minus. You could have a negative curvature as well. Okay? But we can, for us it's sufficient to consider the positive curvature. And the tau is going to be b omega over a square omega square plus b square. This is what that you're going to get. Okay? So I would like to give you some observations. Imagine b equal to 0. What does it mean? So it means that your curve is a plane curve. The curve is a plane curve. And if the helix you kind of collapse it down into the plane, it's going to be a circle. So you will be moving in circles actually. And you can observe it also from here actually. So if the b is 0, then the torsion is 0. Okay? And if b is 0, then k is going to be what?
1 over a.
1 over a, which is the radius of the circle. So it makes sense. So it makes a complete sense. In general, take the ratio of
plus
kappa
minus.
to tau.
So curvature की plus minus interpretation क्या होगी?
The interpretation is ये होगी. So usually we take, what do you call? Usually we take what? So usually we take positive curvature as a positive quantity, but you can also take, what do you call curvature as a negative quantity as well actually. So it's like, okay, something is curving positively as per our expectation, or it is kind of showing us a reflexive behavior actually. Okay. So don't worry about the minus. Take that as this quantity.
Define this as a norm of something.
Something here we can't take that as a negative quantity, but if we do not define that as a norm and we say that okay,
It's plus minus now.
you have this plus minus norm actually. Okay.
And sir, how we can compute this?
How we can compute all this?
Bidirectional.
No, you have the formulas. I just wrote the formulas. Yeah, the formulas. So you always have to use these formulas for computing. So since you have to do the simple calculations, I have done. So the next key observation that I would like to make is that you take the kappa over tau. So take the ratio of kappa over tau. What are you going to get?
A omega.
So you're going to get
B omega.
A omega square over b. Okay.
B omega.
Sir, omega is sir.
Okay,
Huh?
square. Square खत्म करना.
Okay, so you're going to get this. And you see that this is a constant. Isn't it? This is a constant. And we say it's a fixed constant.
They were also constants.
I'm sorry.
Kappa was a torsion constant.
They are constants. So their ratio is also going to be constant. Okay? But they can depend on S actually. In general, practical. So I'm saying that if you take the b equal to 0, it means that you're going to get 0 here, and you have a cos some angle and a sin some angle, so you have a circle. So that will become a circle. Okay? So if you take the projection or a shadow of a helix in xy plane, it's nothing, it's just a circle.
For a given circle, curvature constant होगा.
Yes.
Given circle.
Yes. So it always also follows from this that, if you take b equal to 0, then omega square and omega square will cancel out, and you're going to get 1 over a. And 1 over a is what? It's the radius of the curvature of the circle actually.